shear transformations. So each square here is an element that is that can undergo one of these shear transformation under the external loading. When it does, it essentially becomes a fluid, so it does not support stress anymore. And the stress that it is supporting is redistributed over the neighbors in a very anisotropic way, as pointed out by Bach and Rukov. Yes. Okay. So if you look at a typical element, this would be perhaps the stress history that you would see on a typical element. You have elastic loading. At some point it fails and behaves as a fluid. Then it's loaded again, perhaps until a slightly different threshold, etc. So that would be the time evolution of the stress in one typical square here. Now this, and it's described by this equation. So the stress here, sigma I in one of the squares, increases according to the external loading, but also you have to realize that the external loading is supplemented by the stress that is coming from other elements that potentially have plastic activity. So the redistribution of stress is carried by this propagator, this anisotropic elastic propagator, and this is the typical formula that comes from elastic theory. And so this propagator is very anisotropic, and it has positive and negative contribution, and this is perhaps where what Karen was mentioning, that this kind of model is different from what she was talking about, in which the coupling between elements is always positive. And now the rule that describes the failure here and the yielding phase here is given here. So the plastic rate for one element that comes in here is 0 when the element is elastic. And then in the yielding phase, it can be described, I mean, you have choices, but it can be described as if the element was actually a viscous liquid, okay, which is what is written here. Now you have to decide on one more rule, which is when exactly the plastic phase here will stop. And this can be, for example, you could decide that the site will become elastic again after a typical plastic strain here. It could be a typical time as well, so there are choices here. So these elements here are quite universal in all models that have the same ingredients. The rule for becoming elastic again, so the duration that fixes the duration of the plastic phase, this can be, I mean, this is one of the rules of this kind of automata that can be modified and lead to different behavior. So for those of you who are interested in these models, we have a quite complete review that was published last December in Review of Modern Physics on this. So now let me say a few words about the simplest mean field analysis you can make of this kind of model. And this was actually done a long time ago by Hebrew and Lequeux. And I was told it's actually also used in neural networks models, so the same equation. Essentially, by mean field here, I mean I want to describe the time evolution of the probability distribution of the stress variable on a typical site. And so the time evolution of this probability distribution function is given by a relatively simple equation. So the time derivative here is given by the loading term. This is the external loading that in the previous slides was here. Okay. Then you have a second term, which is the most important one in a sense, and that comes from the fact that comes actually from the second term here in the equation. So a given site here is receiving kicks, positive and negative kicks, from all other sites that are behaving plastically around it. And so these kicks in the rather mean field simplified description will be described as a diffusion term on the stress variables, because they can be positive or negative. Then you have a term that tells you that the site will yield above some yield stress, and a term that it tells you it will be reset to 0 after yield. So this is rather simple. And then in order to close the equations, you have to specify the yield rate. So that's relatively straightforward. I mean, you may assume, for example, that the yield takes place over a time scale tau. And the most important ingredient here is actually that the stress diffusion, so these random kicks, are themselves proportional to the number of sites that are yielding at any given time. So this actually gives you a nonlinear equation. So this looks like a Fokker-Planck equation, but with a nonlinear self-consistent contribution associated with this feedback of the stress of the plastic activity on the stress diffusion. So this equation can be solved analytically, at least in the stationary regime, and it leads to a behavior which is very similar to what is observed in experiments, so that if the coupling that defines the self-consistency is smaller than a critical value, then the stress is given by a yield stress plus a power law of the strain rate with an exponent 1/2, which is not so far from what is observed experimentally. So there are variations of this model. The most important one, and that I would like to point out, is the work by Lin and Viard, who pointed out that actually stress diffusion, in fact, if you take this elastoplastic model seriously, has to be some kind of anomalous diffusion, and this will actually make the model a bit more complex and introduce different critical exponents and critical behavior here. But I will not go into the details of that. Let me just say one word about the previous talk, so the talk of Karen. So if you rewrite the equation for the stress versus the strain as a critical law, then it is very suggestive that you have a dynamic transition which is second order, and then you may expect universal critical behavior, etc., and avalanche behavior with critical exponents, etc. So this will be discussed, this has been discussed in the talk of Karin, and certainly will be also discussed by Ezequiel Ferrero next Wednesday, I guess. Now, what I want to concentrate on is a different regime in which actually you do not observe critical behavior and avalanches, but really you observe a kind of first-order dynamical phase transition in which the system consists, so this is the discontinuous scenario of the yield phase transition. The system actually in flow has coexisting regions that do not flow and are sheared here. Okay, and this type of behavior can exist and is observed in many different systems. And it's usually, in this framework, it's usually associated with the fact that the flow curve, which I was describing as a monotonous flow curve in the previous discussion, is actually non-monotonous. So if you look at the stress versus strain rate, you have a flow curve that has a yield stress here, but then the stress decreases when increasing strain rate. And it is well known that just from continuum mechanics, this part is unstable. So if you try to impose a strain rate which is between 0 and gamma dot c, the position of the minimum here, then necessarily you will have coexistence between a part that is not flowing and a part that is flowing at the same value of the strain of the stress. Sorry. Okay. And it turns out what is interesting about this is, as very often, I mean, second order is more or less universal, maybe, but first order, there are many different ways of creating a first order phase transition in a sense. And this is what I will try to illustrate now with three different possibilities. So one possibility that was advocated for creating such a non-monotonous flow curve is the following. If you look at the stress history of a given element, so as we have seen, it has loading phases, unloading, then it stays fluid for a while, then it becomes elastic again. And now what Cousteau and Overlay suggested is that if the time the system stays fluid becomes long enough compared to the strain rate, then it's very easy to show by simple averaging argument, very mean field, that actually the flow curve becomes non-monotonous. So this is a purely, I mean, average, basically you take the average between the phases of elastic loading and the phases of viscous flow, and you weight them with the corresponding times, and you find these flow curves. So this gives non-monotonous flow curves, but it suggests that obviously this is a mechanism for strain localization and coexistence. So we have checked that in more realistic models, so if in which you actually have interaction between elements, then this also works. And so if we play with the life cycle with the healing time for the time it takes for a block to become elastic again, then it actually leads to non-monotonous flow curves as predicted by Cousseau and Overley. And more interestingly, associated with these non-monotonous flow curves, we indeed find a very strong localization of the strain in a band here that you can see. So this is immobile, and then all the strain, all the velocity is within the red band here. Okay, an interesting point here is that actually, in order to observe this localized band, it's not enough to have this long healing time. It's also important that you use the proper elastic interaction. And if you use an elastic or an interaction between sites that doesn't have this soft mode, these horizontal modes as an eigenmode in a sense, then you find something which is localized but very transient. So you have patterns of plastic activity, but they remain very transient and do not organize in the form of a shear band. So this suggests that if you introduce disorder in the elastic propagation, then you will actually stop the propagation or the establishment of the shear bands. Okay, another mechanism that would probably have been discussed by Damien is one which is associated with aging. So I will not discuss it here, but it has been shown by Damien and coworkers, and also at the microscopic level by Michael Fogg and Shi, that if you have an aged sample, then this aged sample will undergo more easily strain localization. And probably Ludovic Berthier will also discuss that in a sense. So now the last mechanism I would like to discuss for strain localization is actually the effect of inertia. And this is something that was discovered by Salerno and Robbins some time ago, actually not published, but it's mentioned in the PhD of Salerno, in the PhD manuscript of Salerno. And we actually went beyond that and studied it a little bit in detail. And now I will come back to the microscopic view, in which we have particles that are undergoing Newtonian dynamics that are coupled by some potential, interaction potential. They have some friction and there is some noise. And so I will consider two different limits. The overdamped limit, in which this damping is strong in a sense compared to the vibration in the potential, and the underdamped limit, in which the damping is small. Okay? So if I am in the overdamped limit, then everything behaves as I described before. So like the elements, the particles behave very much as the elements I was describing before. And we observe a flow curve, which is a kind of Herschel-Berkeley flow curve with an exponent close to 1/2. So this is the square root of W here, and W is just a non-dimensional strain rate. Okay, so this is at 0 temperature, essentially an athermal system like I was describing before. So it's very consistent with elastoplastic models, and actually you can do it also with elastoplastic models, finite elements. Now, if you introduce temperature and noise, well, quite reasonably, you find that you have a similar flow curve at higher temperature, except you now have a smaller yield stress and a smaller value of the stress for a given value of the strain rate. So that's logical. So as a function of temperature, you have, for overdamped system, you have a family of flow curves that are all monotonous and with a decreasing plateau value as a function of temperature. Now, if you look at an overdamped system, then the surprise that was first found by Salerno and Robbins is that you actually have a non-monotonous flow curve. And this you can, in fact, explain in a rather simple way by saying that the vibrations that are associated with inertia in a system that is underdamped actually play the role of a temperature. Even at 0 temperature, the particles, due to inertia, will have a finite kinetic energy, and this will play the role of a temperature. So as a result, when you increase the strain rate, here, starting from here, then the system will visit curves that belong to higher temperature, and so this will be a weakening mechanism that will lead the stress to decrease here, and then, of course, at high strain rate to increase again. And so this is the mechanism that one can actually quantify in some detail. So the stress is at some value of the damping here in underdamped system is given by the stress in overdamped system at a finite temperature. And so this finite temperature is itself proportional to strain rate, which gives rise to the weakening. So this can be made quite quantitative, and it works well. And even more interesting is that you can actually, having understood this, you can actually go to the continuum description, and so write the stress as a function of gamma dot and some temperature in this form. So with a yield stress that depends on temperature, a prefactor that depends on temperature, and gamma dot here to some exponent alpha. And then you can do a continuum analysis of the shear bands. Okay, so the velocity along x here, you write the force balance, and this is the derivative of the stress with respect to z, the component here. And so you can then develop this by introducing also the temperature field, and you can assign a diffusive dynamics to the temperature field here, as illustrated here. So this is a sink that is associated with local collisions, and this is temperature diffusion, and this is the external, this is the power that is produced by the flow, local flow, locally, the power density. And so this analysis actually predicts that the flow is linearly unstable if the system is big enough, okay, above some critical lengths. And it also, so below this critical length, and this is why in molecular dynamics simulation, the formation of shear bands is not always observed, is that below this critical length scale, then the heat diffusion is efficient enough, and it actually destroys the permanent shear bands. So you cannot establish the critical shear band in too small systems, but in large systems, the shear bands do exist, and the full nonlinear analysis of these equations predict that they are actually stationary and stable solutions. And this can be confirmed quantitatively, and so you will probably, we have a paper on this with Vishwas, and maybe he will talk about this during the week. I should also say that the inertia has actually, and this was also studied by Mark Robbins and Salerno, it also has an influence of the distribution of avalanches, which becomes quite different from what it is in overdamped system, with a peak. Okay, last point, and creep. So creep in this context is different from what people usually mean by creep in pinning. Creep here is applying a stress to a system and waiting and see whether it starts to flow or not. And what is known from experiments is that the answer to that is very dependent on system history and age. So these here are 3 different values of the stress. This is the strain as a function of time, for 3 different values of the stress and different values of the age of the system. And so depending on this, you see that the fluidization time varies quite a lot, and also whether the system actually starts to flow here or not also depends on the level of stress and on the age. So the only point I want to make here is that we can reproduce the same type of behavior using the kind of elastoplastic models I was describing before. We can reproduce the dependence on age of the system, but also, and Chen Liu will discuss that this week actually, fluidization is announced by strong cooperation, and the fluidization time is very non-universal as a function of the state of the system. So it's, you can't find some kind of power law that describes fluidization time as a function of the distance to yield stress, but this is very dependent on the preparation of the system. Okay, so let me just summarize here and thank all the people who have been involved in this work and you for your attention.
Quick questions?
In the model you described to form this shear band, what does control the finite thickness of this band? Which kind of length scale is emerging to which thickness, or does it go to zero thickness at this? So what do you mean? The thickness of the thickness of the
I think you want the total, right?
Yeah.
Total.
When you start to reach to localize, you localize the band. Well, in fact, it's very dependent. So you could say, if you look at a curve like this, so if you take a strain rate here, okay, you can have different solutions for coexistence, in fact. And what determines this, which solution is chosen, seems to be very dependent on the precise mechanism. So for example, that's something we have studied. I mean, the case we have studied most is this one, these coupled equations. And then you can see that there is no real simple rule. It's really the stability of the solution. So there's no lever rule that gives you a priori the width of the band. The only thing is, of course, the total strain rate. I mean, the total strain rate has to be given by the integral of the strain rate over the band. But you have several different solutions, and it's really a I mean, there is no simple like thermodynamic lever rule that would give you the thickness.
Writing first order phase transition is the same. I mean, the area you find in the totally undetermined unless you go atomistic.
Yes, but in first order, I mean, you have some Maxwell rules that tells you the coexisting phases are. Yeah, but still, I would compare this to the Maxwell rule in a sense. Okay.
The analysis that we talked about here, shear banding is when you have stable shear bands in flow, right? And you mentioned the work of Shi and Clark and I guess subsequent works. So there, whether you form a shear band or not is something that's looked at under quasi-static conditions. So it's and again, there's no temperature there except the structural temperature that corresponds to how
Yeah.
so it's very unclear that these considerations will also apply when we look at sort of yielding under quasi-static conditions when we form shear bands.
So you mean the relationship between the stable shear bands and the transients that you have when you have a stress overshoot? I agree this is not, I mean, probably Susan Fielding will discuss that as well, but I agree there is no well-established and probably no general theory for connecting those. I mean, you have to go into the details of every system, I think.
So your expression for the force balance, you're assuming that the viscous drag is proportional to the local velocity, right?
Do I? Well, that's just force balance.
No, but you're saying the viscous drag is proportional to velocity rather than something like Laplacian velocity, right?
No, here, I mean, there's no viscous drag here. Okay. I mean, this is just the flow curve, and this is just force balance. There's no. Well, here I'm only considering stationary solutions, so we. No, I mean, what I tried to show, maybe, sorry if it was confusing, is that there are really quite different mechanisms that can lead to strain localization. And so this temperature diffusion is one of them. Aging is one of them. A long healing time, whatever this means, is one of them. And presumably in many cases you have a combination of everything. So, or even, so, sorry if this was confusing, but here there's no aging. It's we haven't. It's essentially stationary flow.